Hello, today's class will be graph-based algorithms for test case generation. This is a topic in software verification and validation, and in about 10 to 15 minutes we are going to discuss this topic. So just to remind you to subscribe if you have not done so for more lessons on software verification and validation. Let's get started. In this lesson we are going to discuss applications of graph-based algorithms. We are going to look at algorithms for transition coverage. We are going to look at the example, and then we're also going to look at graph-based algorithm for transition pairs. We are going to look at an example also, and then we are going to consider graph-based algorithm for concurrent testing, and then we are going to look at an example. So what are the applications of graph-based algorithm? We have about 5 I can think of. One, it can be used in control flow representation. Graph-based algorithms can also be applied in communication protocol, in embedded controllers, in user interface systems, and in web-based application. So what are these algorithms? Basically, we are going to look at 3 algorithms in this lesson. One of them is graph-based algorithm for transition coverage. We are going to look at Euler's graph. The second one is graph-based algorithms for coverage of transition pairs. Remember transition pairs. And the last one we are going to look at graph-based algorithms for concurrent testing. So let's get started with the first one. Now we have graph-based algorithms for transition coverage. The problem is described as New York sweeper problem. An algorithm that can be used to thoroughly cover the transitions in a state diagram. So the objective here is to cover all transitions by test sequence and return to the initial state. So what is the approach? The approach is that you have a directed graph. You need to find the shortest path that covers all transitions and goes back to the initial state. For this example I have here, think of these 3 coverage, think of these 3 parts I've written here. We have A, B, C, B, F, E, G, D, E, G. Let's look at it and see if it works. A, B, C, okay, B, F, E, G, D, E, G. So it thoroughly covers it, but let's look at the algorithm itself. How the algorithm works. The algorithm has 4 steps for Euler circuits. 1. Find the polarity of the nodes. Okay. Second, duplicate the edges that lead from one node with positive polarity to the node that have negative polarity until all nodes have 0 polarity. Now, how do you find the polarity of a node? The polarity of a node is a number that is calculated by plus incoming nodes, incoming edges to that node, minus outgoing edges. We are going to look at the example and it becomes very clear. At the end, you obtain Euler circuit for the resulting graph. Then go ahead to traverse the Euler circuit, and that defines the test sequence. Let's take an example of how this works. Alright, we have this initial example we used in the first example. This is the original graph, but now I have added polarity to it. How do I get this -1? We have incoming is +1 minus outgoing -1 -1, because we have 2 outgoing, so you have -1 -1 +1. That gives us -2 +1, and that is -1. Let's look at this. We have +1 +1 -1. For this outgoing here is minus, and that gives us +1. Okay, look at this. We have -1 -1 -1, that is -3 +1 +1, that gives us -1. Okay, this is the first step. The second step, take note, the second step is that you need to duplicate the edges. So if you have this +1 here, it means that you have to add another outgoing edge, to this place, so that it can negate it and it becomes 0. So at this point we have added an outgoing edge from this node plus one node outgoing to this node. So that is what we are going to do, and if that happens, we now have 0 because we now have additional minus 1. So that is how we continue until all nodes becomes 0. If we have done this, we have reached to the ends of the modification of the graph, and then we go ahead to traverse the graph, and this time we just have one sequence: A, B, C, D, F, E, G, D, E, G. So that is the procedure for Euler's circuit graph-based algorithm for transition coverage. If this is not clear, pause the video and try to get this around your head. Let's now look at graph-based algorithms for covering transition pairs. This is sometimes referred to as safecracker sequence. The objective is to cover transition sequences so that all possible sequences will be covered and the test gets back to the initial state. The steps is find shortest path that includes all possible sequence of n subsequent edges. Take note, the transition is covered in pairs. So let's see, it means you must cover two transitions at a time. Let's look at the algorithm. It's called the Bruin algorithm. First, construct a dual graph. You already know how to construct a dual graph. That is what we've discussed. Now the steps, this is the steps to construct a dual graph. The edges of the original graph are mapped to nodes. Let me show you what that means. So now you have, for instance, we have edge A here. It means that in the dual graph, A will be a node. So let's continue. If there is a pair of subsequent edges in the original graph, then an edge is drawn in the dual graph between the two nodes that represent these edges. This is the same as mapping the edges to nodes. Then you go ahead to create a Euler's graph, which is what we already know. So we talk about dual graph here, and we talk about Euler's graph in the first algorithm. So when you create a Euler's graph, you have Euler circuit, and that will help you define the test sequence. Let's go ahead to look at an example, and that will help us get it clearer. Alright, this is the original graph, this. Now we have A is mapped to a node. So instead of being an edge, it's now a node. Now we have from A, we have a transition to B. Okay, so we have A to B. What is B? B is also a node. E is a node, and so on. So all the edges are mapped to nodes, and then we have transition between the pairs of the edges. So AB, from A to B, it means two transitions, as you can see. In the original graph is two transitions. Here you have this transition, and here you have a second transition. So, but in the dual graph, you just have one edge. Let me use this pen to try to highlight what I'm saying. Alright, so you have, this is the dual graph. Take note that the edges now becomes nodes. And for a node to exist, there must be, for an edge to exist in the dual graph, there must be two pair of transition mapped to one transition. So we have A, transition A, and B mapped to this transition from A to B. That is why we call it transition pair coverage. So after you do this, then it means you've done the first part. Then you go ahead to create a dual graph, just like the Euler's graph. So you go ahead to now sequence through the transition to cover all pairs of the transition. So here you have A, B, you have to C, B, F, E. If you follow this transition here, then you see that the whole sequence of transition is thoroughly covered. So maybe pause the video and try to practice it by yourself. Maybe you try to close the dual graph, and try to construct it from the start by yourself. You appreciate how interesting this is. Alright, let's move to the third algorithm, and that is graph algorithm for concurrent testing. In this case, the test is carried out by concurrently by number of testers, not just one or more testers at this time. So the objective is a complete transition coverage so that all the testers share in the testing task and complete it in the shortest time. The steps is that all testers begin at the start state, and the tested system should be able to reset back to the initial state. The approach or the problem sometimes is called street sweepers brigade. So this is the algorithm. I'm not going to read all this, but try to take time to read it until you get used to it. I'm going to explain this algorithm with the example. Alright, so this is concurrent testing coverage example. So the first step is to choose a number of testers. This time we have 2 testers. Then you now have to choose test sequence, the first test sequence you need to choose. At this time we choose K to be 7. It means that the first tester will carry out a test that covers 7 transitions. Then the remaining transition will now be handled by the second tester. And that is this first scenario here. You have A, B, C, okay, then coming back to B, F, E, G. Okay, that is the first transition, that is K is equal to 7 transitions, and then but now this D is not covered. It means that the second tester will now cover D, E, G. So it starts from here, D, E, G. So with these 2 testers, the transition is thoroughly covered completely. Now we have a second scenario where we choose K to be 5. So if we choose K to be 5, let's say A, B, C, B, G. A, B, C, B, G. That covers one part. The remaining part can now be covered by the second tester starting from D. I hope this is very clear. So this is how concurrent testing works. Now we've covered 3. We have transition coverage, where we discuss the New York street sweeper problem. We have covering transition pairs, where you need to obtain a dual graph. And now we have concurrent testing, where you have to use 2 or more testers. Alright, let's now summarize. We discussed transition coverage, and then we discussed coverage of transition pairs, looking at the algorithms, and then we discussed concurrent testing. So these are the 3, and I gave examples of these 3. So this is where I'm going to stop for now. If you have any question, any homework you need me to do a presentation, leave it in the comment box, because my videos and presentations are based on requests from my subscribers and my viewers. So just leave whatever question or homework you have in the description box below. If you like this video, give it a thumbs up. If you have fellow students that may need it, you can share it around with them freely. Remember, I'm giving free lessons on software verification and validation. Just remind you again, if you've not subscribed, just click on the subscribe button to get more videos on software verification and validation. I would like to thank you for viewing.